Hello everyone, this is Matt with Zanger. Welcome back to our AP series. In today's video, we will connect two ideas, differentiability and continuity. To check whether a function is differentiable at a point A, we can compare the derivative from the right side and derivative from the left side. The first formula is read as the limit as h approaches 0 from the positive side of fa plus h minus fa over h. This is the right-hand derivative at a. The second formula is the limit as h approaches 0 from the negative side of fa plus h minus fa over h. This is the left-hand derivative at a. The important rule is a function is differentiable at a point if and only if the left-hand derivative and the right-hand derivative both exist and equal. So if the slopes from the two sides are different, the function is not a differentiable there. This slide gives us the main relationship. If a function is differentiable at a point, then it must be continuous at that point. And if it is continuous at that point, then the limit at the point exists. So the direction is differentiable, continuous, and limit exist. But we have to be careful. The reverse is not always true. A function can be continuous, but not differentiable. So continuity is required for differentiability, but continuity alone is not enough. So if a function is differentiable, then it is definitely continuous. That is like the first bike knocking down the next one. But continuous does not always mean differentiable. A graph can be connected without having a clear tangent slope at a point. And if a function is not continuous, then it cannot be differentiable. Differentiability is a stronger condition than continuity. Here we have an example, fx equal to absolute x minus 2. At x equal to 2, the graph has a sharp corner. On the left side, the slope is negative 1. On the right side, the slope is 1. Since the left-hand derivative and right-hand derivative are not equal, the derivative does not exist at x equal to 2. So even though the graph is continuous at x equal to 2, it is not differentiable there. The key idea is sharp corners or sharp turns usually mean the derivative does not exist. In this example, the function is fx equal to x to the power of 1 over 3. The graph is still continuous at x equal to 0. There is no break or hole. But at x equal to 0, the tangent line is vertical. A vertical tangent line has undefined slope, because the slope becomes infinity steep. Since the slope is undefined, the derivative does not exist at x equal to 0. So this is another example where the function is continuous, but not differentiable. The main takeaway is differentiability is stronger than continuity. If a function is differentiable, it must be continuous, but continuous function may fail to be differentiable because of a corner, cusp, or vertical tangent.